Introduction to SQL for Banking Analysts. In banking, data is everywhere and SQL is the tool to unlock it. As an analyst, you will need to explore transactions, spot trends, and generate client reports. This lesson will teach you how to use SQL-like syntax in Python for real-world banking problems. You will start with synthetic banking data and apply practical queries step by step. By the end, you will be able to answer business questions about accounts, customers, and transactions. Running the cell now. Let us get ready to work with data and SQL-like queries in Python. We import pandas so that we can work with tables of data. We import NumPy for efficient number work and random sampling. We also import warnings to avoid distracting warning messages. Let us ignore warnings so results are simple to read. Running the cell now. Practice. What is your favorite thing to analyze in banking data? Write it down. What data are we working with? Our core datasets are transactions, customers, and accounts. Transactions track movement of money with customer, type, amount, channel, and time. Customers hold basic info like segment and region. Accounts join customers to specific products. A common beginner mistake is mixing up columns during joins or grouping. Running the cell now. Now let us create a synthetic transactions table to practice with. Set C to 42 for reproducibility so results remain steady. We declare how many transactions we want to create. We set how many customers to use across transactions. We create a table to hold our transactions. We assign every row a unique transaction ID. We randomly choose which customer performed each transaction. We create realistic amounts for every transaction. We randomly choose whether each transaction is debit or credit. We randomly assign a channel for each transaction, like ATM or online. We generate a date and time for every transaction. Our table is ready, let us print its shape to check size. Let us preview the first 3 transactions for a sense of the data. Running the cell now. This output shows our simulated transactions dataset with 1,000 rows and 6 columns capturing key details like customer IDs, amounts, transaction types, channels, and timestamps. Notice how the customer IDs repeat across transactions, reflecting multiple transactions per customer, and the amounts vary around a mean of 150 with some spread. This setup prepares us to analyze transaction patterns and link them to customers and accounts in later lessons. Try, can you spot which fields are numeric versus which are text? A strong banking data set always links to customer details. Create a series of example customer IDs. Make a customers table holding all those customer IDs. Add the segment each customer belongs to. Most are retail, some are business. Detailed region info helps with analysis. We balance metro and regional. Print out how many customers there are for review. Preview a few records to see the data structure. Running the cell now. This output shows that our customer's data frame contains 200 rows and 3 columns, customer underscore ID, segment, and region, aligning with our intended structure. Notice the first few customers are labeled as retail segment and located in the metro region, reflecting how we segmented and regionalized our customer base. This confirms we successfully created a foundational dataset to link customer info with transactions and accounts later on. What segment do you think would be the most valuable for the bank? Discuss. Accounts connect customers to products and carry further metadata. Let us create a table of accounts for our customers. Every account gets a unique identifier. Each account links back to a specific customer. Accounts can be savings, check, or credit, randomly assigned. Every account has an open date for time-based queries. Print out total accounts. Preview the structure for a few accounts. Running the cell now. This output shows the accounts data frame has 200 rows and 4 columns, confirming a sizable dataset linking customers to multiple account types. Notice the unique account IDs, associated customer IDs, randomly assigned account types, and sequential open dates. This structure sets the foundation for analyzing how different account products relate to customer activity and behavior. Why is it useful to know the open date of an account in business analytics? Progressive SQL examples in pandas. We will learn to use SQL-like operations in Python with pandas. This means using .query, .groupby, .merge, and .loc to ask business questions. We start with simple queries and work up to joins and aggregations. Running the cell now. Let us start by finding all debit transactions like a SQL select. Where statement. We write a comment to specify the beginner example. We use query to filter only debit transactions from the table. Print out a small sample of the filtered result. Running the cell now. Here, we use .query to filter the data frame for only debit transactions, illustrating a basic SQL-like selection in pandas. Notice the output shows only rows where transaction underscore type is debit, keeping all columns intact to preserve transaction details. This sets the foundation for more complex filtering and analysis based on transaction types. Practice, change debit to credit and compare the outputs. Finding the biggest transactions is something every banking analyst will need to do. This comment describes the purpose of this example. We use Nargis to get top 5 transactions by amount. Display just the ID, amount, and customer for clarity. Running the cell now. This output shows the top 5 largest transactions sorted by the amount column, giving us the transaction ID, amount, and customer ID for each. Notice how we use the .nargist method to quickly filter the highest values, similar to a SQL query with order by and limit. This demonstrates how pandas can perform simple yet powerful data retrieval operations essential for business analysis. Can you modify this to show the channel and date for each top transaction? Let us count how many transactions happened through each channel. This is like SQL group by count. We explain the purpose of this beginner query. We count how many times each channel appears. Print out the resulting counts. Running the cell now. This output shows the count of transactions grouped by each channel, using the .value underscore counts method, similar to a SQL group by with count. Notice how ATM has the highest transaction count, followed closely by POS and branch. This highlights the distribution of transactions across channels, helping us understand customer behavior before moving on to more complex grouping and filtering. Which channel surprised you with its popularity? Comparing monthly debit and credit flows is crucial for portfolio monitoring. We label this as the first intermediate example. Add a month column derived from the transaction date. Pivot the table so rows are months and columns are debit or credit sums. Print the resulting monthly breakdown. Running the cell now. This output shows the total credit and debit amounts aggregated by month, with each row representing a different month. Notice how the pivot underscore table neatly summarizes transaction totals, similar to a SQL group by with aggregation, helping us quickly compare inflows and outflows over time. This reinforces using pandas to perform SQL-like data summarization efficiently. Try changing the aggregation to mean for average transaction size per month. Suppose you want to know which regions drive high-value transactions. Join is key, just like SQL join. Note this example focuses on joining tables. We merge the transactions with customers, linking on customer underscore ID. Show customer, region, and transaction amount for a quick preview. Running the cell now. This output shows the first 3 rows after merging transactions with customer data by customer underscore ID, adding the region column to each transaction. Notice how each transaction now includes regional info, allowing us to analyze sales by area. This join is key for combining datasets to answer location-based business questions using pandas. What happens if you change left to right in the merge? Now let us compare the average transaction size by customer segment. Label our third intermediate example. Merge transaction data with customer segment info. Group by the segment field and calculate the average amount. Print the results for retail and business. Running the cell now. This output shows the average transaction amount per customer segment after merging transaction and customer data. Notice how the dot merge brings segment information into the transaction data, and the dot group by with dot mean calculates the average spend for each segment, revealing that retail customers tend to spend slightly more than business customers. This demonstrates combining datasets and performing aggregated analysis just like SQL joins and groupings. Try, what does the result tell you about customer behavior? A classic business question is, how many distinct customers use each channel per month? We label this as an advanced example. Group by both month and channel, count unique customers, and reshape the table. Print the full breakdown for management insight. Running the cell now. This output shows the number of unique customers using each channel for 2 months, with months as rows and channels as columns. Notice the dot group by with dot unique counts distinct customers, and dot unstack reshapes the data for easier comparison across channels. This example highlights how pandas can replicate SQL's group by and pivot functionality to summarize customer activity by channel over time. Why is customer uniqueness important in channel analysis? You may need to find which products receive the biggest inflows. Let us rank account types by volume of credits. We are working with an advanced example using joins and filtering. Merge transactions with account info to get the account type per transaction. Filter for only credit transactions. Aggregate and find the top 3 account types by total credited amount. Print the result for review. Running the cell now. Here, we merged customer and account data to analyze credit transactions specifically. The output shows the top 3 account types by total credit amount, highlighting that savings accounts have the highest credit volume, followed by check and credit accounts. This illustrates how to combine datasets and perform group by aggregations in pandas to answer business questions about transaction trends. Modify this to see top 3 by debit volume instead. For advanced users, let us compute the running balance for a single account, just like in a real statement. Label this as a third advanced scenario for account analytics. Pick a random account from the merged data. Get all transactions for that account, sorting by date. Create signed amounts, making debits negative and credits positive. Produce a running balance using cumSum for cumulative sum. Print first 10 balances to see the effect over time. Running the cell now. This output shows a running balance calculation for one account's transactions, with credits adding and debits subtracting from the balance. Notice how the balance column is a cumulative sum of signed amounts, demonstrating how to translate SQL-like cumulative logic into pandas. This illustrates combining filtering, sorting, mapping, and cumulative aggregation to answer a key business question about account activity over time. Try, can you find where the account dips into negative balance, if at all? Error handling is vital. What happens if you misspell a column? Let us try a query with a deliberately bad column name. Use a try block to catch errors. Try filtering with a typo in the column name. Catch the error if it happens. Print the error message so we can learn from it. Running the cell now. Here, the output shows an error caused by a typo in the query column name, transaction_typ instead of transaction_type. This demonstrates the importance of using exact column names when writing .query statements in pandas, as even small mistakes lead to errors. Catching and understanding such errors helps ensure your SQL-like queries run correctly and return the expected data. How would you fix this error? Another mistake is merging on the wrong keys. Let us see what happens with mismatched columns. We try merging transactions using customer_ID against account_ID, which will not match. Enclose the merge in a try block. Run the merge with intentionally wrong keys. Handle the error if it shows up. Print out what went wrong so we can learn. Running the cell now. Always check your key columns before merging tables. A banking analyst should always be cautious. Inspect your data before starting analysis. We advise checking the technical info of the table. Get a summary of numeric and categorical columns for a first review. Running the cell now. This output shows an initial data inspection of a 1,000-row data frame with 7 columns, confirming no missing values and mixed data types including integers, floats, objects, and date time. The summary statistics highlight the range and distribution of key numeric columns like amount and transaction_ID, helping us understand data scale and identify any anomalies before applying SQL-like queries. This foundational step ensures we work with clean, well-understood data as we proceed to querying and grouping operations. Try, run info, and describe on customers too. It is best practice to save results for future review or sharing with team members. Create a table with average by segment results for communication. Save this summary as a CSV file. Let your team know the file is ready. Running the cell now. This output confirms that the grouped and aggregated data on average transactions by customer segment has been successfully saved to a CSV file. Notice that using .reset_index prepares the data frame for export by flattening the grouped index, making it easy to share and analyze results outside of pandas. This step ties into the lesson's goal of performing SQL-like data manipulation and then exporting key insights for broader use. Let us open the saved CSV to inspect the average transaction by segment results. Now, open and check the output CSV visually after running this cell. Let us solve a common banking problem end-to-end. Who are the customers spending over $10,000 in a month? First, group all debit transactions by customer and month, and sum the debits. Select customer month pairs where total is above $10,000. Join back to customer details for context. Display which customers, on which months, and their segments and regions. Running the cell now. This output shows an empty data frame, meaning no customers had debit totals exceeding $10,000 in any month. This highlights how the code filters and aggregates transactions by customer and month, then flags high-value activity, illustrating the power of grouping and filtering data to answer targeted business questions. It also shows the merge step adding customer details, ready to identify key segments or regions if matches were found. This is a typical flagging case for compliance and business review. Subscribe on YouTube for more lessons like this. What have you learned? How to use SQL-like logic for banking analysis in pandas. How to clean, join, and aggregate real banking datasets. How to find business answers using code, not just formulas. Practice these patterns every day for true expertise. Watch our videos for practice challenges and advanced tips. Running the cell now.